All right, so 8.3 is all about equivalence relations. Okay, equivalence relations, and then we're also going to talk about equivalence class relations, which is similar but slightly different deal. Okay, so equivalence relations, this is a big deal. For that to be true, okay, the relation must have reflexive, symmetric, and transitive properties. Okay, so R is an equivalence relation if and only if these three things are true for it. Okay, remember, if and only if you can show those three things are true, then it is an equivalence relations. If I tell you it's an equivalence relation, those three things are true. Okay, that is the big takeaway from this chapter, or from this section rather. Okay, so let's do an example of this real quick and then see what you think about it here. Okay. Okay, and so in this situation here, for instance, one more thing I wanted to mention here before I get to another example here is this. The idea of a partition. Okay, so you could have a set. Okay, and then you can partition that set. So a partition might look something like this: the evens and the odds. But together, the union of those two sets, union being the evens, if you put them together with the odds, they equal the entire set. Okay, the entire set. Okay, so you can partition it off. Okay, so anytime you do that, that's what's called a partition. So you can do that. That'll come up today in our lesson because we can, if we partition some of these guys, we're going to look at them. Okay, now it's a pretty straightforward process once you get going there. Okay, we have equivalence relations. That is all there is to it. Once you understand what an equivalence relation is, then we can kind of go crazy from there. Okay, so again, what are you going to be asked to do? You're going to be asked, is this an equivalence relation? Or knowing that it's equivalence relation, what do you know about it? Okay. Okay. And then we take that another step further, and we talk about equivalence classes of an equivalence relation. Okay, so suppose A is a set. Okay, and R is an equivalence relation on A. Okay, cool. That's easy. The equivalence class of A, notice it's little a, which is denoted by that's the equivalence class of A. Okay. Getting cold there. Is the set of all elements. What happened here? Is the set of all elements X in A such that such that X is related to A by R, not little a, sorry. Okay? And so it's read like this. The equivalence class A is equal to, squiggly brackets, X, that are elements of R, elements of A, you idiot, such that X, R, A. Okay? Jake, can you give us an example? Gosh, I'd love to. Here you go. Here is one right here. Mm-hmm. There's my A. Cool. What I would like to know is, can you give me, let's just say R is equal to, R is defined rather as, let's see here, such that X and Y are elements of A, and such that 3 divides X minus Y. Sure, let's do that. That sounds like a good one. So that's what R is, okay? So what we need is, we need the values of these guys where this forms an equivalence class. So let's look at them here for a minute. So 2 minus 1 is 1. That doesn't work. 5 minus 1 is 4. No. 7 minus 1 is 6. So there you go. So 7 and 1. Okay. 9 minus 1 is 8. No. 13 minus 1 is 12. So that'll work. 14 minus 1. No. What do we got here? 5 minus 2 would work. 7 minus 2. No. 9 minus 2. No. 13 minus 2. 14 minus 2. 14 and 2 works. Cool. 9 and 5, no. 9 and 7, no. Wait, what am I doing? 9 and 5, no. 7 and 5, no. 9 and 5, no. 13 and 5 is 8. 14 and 5 is 9. That'd work. What do we got here? So you got 9 and 7, no. 13 and 7, yes. 14 and 7, no. 13 and 9, no. 14 and 9, no. 13 and 4, no. That's it. So it's those guys right there, okay, where the difference is divisible by 3. Are you with me? Now, question. Can you flip-flop them? Does this work? Does this work? The answer is, of course, yes. What does that tell me? It tells me that it is what? That it's symmetric. Okay, cool. 1 and 7 work. 1 and 13 work. Does that mean that 13 and 7 works? It does. It does. Does that work for all of them? No, it doesn't. So the transitive property fails here. Does that make sense? And so in this case, that wouldn't work, all right, for this equivalence class. They divide by 3, okay, but the fact that it divides by 3, you can flip-flop them and it's symmetric, but for instance, does the 1, 1 show up? No, it does. 1, 1, oops, 1, 1 would show up, 1, 1, sorry, 2, 2, 5, 5, all these guys would show up, dot, dot, dot. So it is clearly reflexive. It is symmetric, but it's not transitive, okay? So like 1 and 7 works, okay? And 13 and 7 work. Does 13 and 1 work? Yes, it works for that one. 2 and 5, cool. 14 and 5, yes. So you'd have to make sure that they all worked. I don't think all the transitive ones work here, okay? And so that doesn't work, I think. You have to draw the picture out. Let's draw the picture. Here's 1, 2, 7, oops, 5 rather, sorry. 7, 13, 14. So let's draw these guys. Clearly they are all reflexive. Nice. And we've said that they are clearly symmetric. So I can draw this arrow. It's bidirectional. Oops, 14 and 1 doesn't work, you clown. Sorry. 14 and 2 works. That does, sorry. 14 and 5 works. 5 and 2 works. Cool. Both ways, of course. 13 and 7 works both ways. And 13 and 1 works both ways. And 7 and 1 works both ways. Cool. So again, everything we have drawn up so far is symmetric and reflexive. Okay. Now, does it hold for the ones that are here? Yes. So 1 goes to 7, 7 goes to 13. Yes. 2 to 5, 5 to 14. Yes. 2 to 14, 14 to 5. Yes. They all work. So the ones that are matched up, this 100% does work. So this is what we call an equivalence class relation. Okay. And the idea being is that this one works because they're divisible by 3. This is a partition. This set of pairs, this set right here, okay, which, again, I didn't include all of those. You know they're there. And I didn't include all of these, which are just backwards, the other ones. Those guys right there is a subset of what we get coming out of the A here, okay? And that's a subset of it. And that subset, some of them work, some of them don't work, okay? And nice, okay? That's the equivalence class from that set of A. Okay, we will see some other ones here, and here's a couple of more examples of that. Okay, so let's do this one here. So x is equal to A, B, and C. So A is the power set. The power set. Power set. Good Lord, learn this right. The power set of x. Nice. And R is defined on A. R is defined on A as follows. So you're going to have for all sets U and V, for all sets U and V in the power set, okay, U or V is defined such that the number of elements in U is equal to the number of elements in V. Nice. Cool. So remember, the power set is the empty set, and then it's A, B, C, A, B, A, C, B, C, A, B, C. Right? That's a power set. So let's look at this here. Now, that's the deal. What they ask us to do, they want to know the relation R is an equivalence relation on set A. Find the distinct equivalence classes of R. Cool. All right. So for when the number is equal to 1, it would be A, B, and C. Okay. So in other words, those would be the three that would show up in there. Just those three. Remember, those are a partition of this whole power set. You with me? And so you could do A, B, of course. You could do A with itself, obviously. You could do A with C, obviously. You could get because it's an equivalence class, of course, you have to do them backwards too. Now, I'm not going to mark AA because AA is itself, but BA has to be flip-flopped around. Then you're going to get BC, of course, we haven't talked about yet, and you're going to get CB, which, of course, we haven't talked about yet. Okay? And then, of course, BB and CC. Okay? That would be the equivalence relation set of n equals 1. That would be the equivalence class of n equals 1. If you got n equals 2, n equals 2, so the number of terms is 2 in each of them, what would you end up with? Well, you would end up with AB, AC, and of course then you'd have AB with itself. And then, of course, you'd have AC with itself. And who else? A, B, and AC, and is that it? That's it, right? I think that's it. Oh, I got to flip-flop these guys. AC, AB. That should take care of it, right? I think so. That's great. And then for n equals 3, the only one that's going to be in it, n equals 3, is ABC with ABC, right? Nice. Yay. Not too difficult. Okay. Let's do this one here. This sounds like a fun one to me. Cool. All right. So also we need to list out all of the possible equivalence class relations with this guy. So number 12. This is on page 475. So A is equal to the decimal or the integers between -4 and +4. Okay. And R is defined on A such that for all ordered pairs M and N that are elements of A, MRN is defined as, geez, we've done this one before, kind of, Jay. I know, kind of, we have, sort of. Okay, very similar problem. Now, think about this here. Okay? So we need 5 to divide this guy right here. So we need 5 to divide that. So we need to pick out the pairs that make this work. Okay. Now, you can kind of go through and see that, but clearly, you could match up. First of all, we know that this is an equivalence class relation. So all of these guys will be enlisted in there, correct? Because they all going to give you 0. They're all going to be able to get matched up with their counterpart on the other side and the reverse of their counterpart on the other side. But because that is part of the equivalence class, it's symmetric. Okay? Then, think about this. We need to be divisible by 5. So 16 minus 9 is 7. That is not going to work. 16 minus 4 is 12. So any of the 4s and 2 combinations. Oops. And then, of course, you're like, well, what about positive 4? Sure. So any of those guys and their reversals, if you will, because, again, they are symmetric. Okay. Then, what do we got here? We got 16 minus 1 is 15. That would also work. So any of the 4s and 1 combinations. Would also work, as would these guys. Nice. And then what else? That takes care of our 16. Then we've got 9 minus 4 is 5. 9 minus 1 is 8. I'm going to cut it 9 minus 1. So, okay, so then the 3s with the 0s would work. And vice versa. Right? Is that it? 2 minus 1. Oh, what are you doing, stupid? Never mind. I was thinking divisible by 3. Divisible by 5. Ding dong. 16 minus 9. No, 16 minus 4 is 12. Yeah, 16 minus 1 is 15. That's divisible by 5. Okay, great. So then 9 minus 4 is 5. Okay, yeah, that does work. Sorry, my bad. I wasn't thinking. Right? And vice versa. Right? And what else? Is that 9 minus 4? So 9 minus 1 is 8. That doesn't work. And then 4 minus 1 is not 5. So there you go. These guys should be all of them. Okay? So what they want us to do, they want us to list all the following that must be true if R is there. Okay? It's reflexive but not symmetric. Okay? Okay. Oh, I'm sorry. That was never mind. So find the relation is an equivalence relation. Find the distinct equivalence classes of R. Well, we just did. There they are. Okay, and it's a pretty straightforward deal right there. Now, I want to do this one here because this one's kind of fun. If you had 1, 2, 3, 4, 5, sure. And let's do. Actually, let's change those out. Make them bigger. Make it more interesting. Cool. And let's let R be defined as, well, I'm sorry. So yeah, so X, R, Y is defined as X minus Y mod, or I'm sorry, mod 3. Okay? Now think about that right now. There's going to be 4 equivalence classes here. Right? Because those are the possible remainders we could have. So when you think about this, I'm going to subtract biggest minus smallest because that to me just makes it sense. But of course, remember, this is an equivalence class. Because clearly, doesn't matter if I do 46 minus 27 or 27 minus 46, I get the same answer. And it will or will not be divisible by 3. Or I will get the same remainder regardless. So just be aware of that. So let's do this here just for fun, shall we? So let's do the remainder zeros, okay? So the remainder 0 class. Well, of course, 11 and 11. Duh. 14 and 14. 19 and 19, obviously. 27 and 27, sure. And 46 and 46. That's great. Those are the obvious ones, okay? Now, when I subtract, 46 minus 27 is it's 19. That's not divisible by 3 evenly, so I'm going to continue on. 46 minus 19 is 27, and that is divisible by 3, so 46 and 19 works. By the way, so does 19 and 46. Are you with me? Okay. So 46 minus 14 is 32. That is not divisible by 3 evenly. And then 46 minus 11 is 35, which is also not divisible by 3 evenly. These are the only members, I think. Wait, did I mess up? No, then 27 minus 19 is 8. No. 27 minus 14 is 13, so nope. 27 minus 11 is 16. No. 19, that's 5, and that's 8, and that's 3. So 14 and 11. And 11 and 14. All of those will get you either 0 or a multiple of 3 when you subtract. Therefore, when you divide by 3, you'll get a remainder of 0. This is the equivalence class of remainder 0. The remainder 1 equivalence class, okay, would look like what? Well, let's think about that for a minute. Now, of course, the person doesn't want to do this in their head. I'm going to show you can do this in Excel if you'd like as well. 46 minus that is 21. 46 and 27. No, it's 19. 19 divisible by 3 gives you a remainder of 1, yes? So 46 and 27. And of course, 27 and 46, because again, it's equivalence relation. Okay? What else we got here? 46 minus 19 is 27. That doesn't count. 46 minus 14 is 32. No, that'll give you a remainder of 2. By the way, I should keep track of these as I go along. That'll give you a remainder of 2. No, that's too much work. I'm not going to do that. All right, so then 46 minus 11 is 35. Is also a remainder of 2. 27 minus 19 is 8. That'll give you a remainder of 2. 27 minus that is 13. That gives you a remainder of 1. So 27 and 14. 14 and 27. Okay. 27 minus 11 is 16. So that would also work, right? That will give you a remainder of 1. 19 and 14 is 5. So no. 19 and 11 is 8, so no. 14 and 11, no. All right, so let's continue on. So I want a remainder of 2. Now I know it can't be 46 and 27. I've already used that. 46 and 19 already shows up here somewhere, yes? So it can't be that. 46 and 14 gives you a remainder of 32. That works. So 46 and 14, okay? And, oh, by the way, you can't have a remainder of 3, Jay. Pull your head out of your buttocks, okay? If it's mod 3, it's 0, 1, and 2 for remainders. I knew something was a little goofy there. Now, let's continue on, shall we? 14 and 46, of course, as well, okay? Let's see here. 46 and 11, that gives you 35. That also works. All right, let's go to 27. 27 and 19. Have we used that one yet? It's 8, so nope. 27 and 19. 19 and 27. Cool. 27 and 14 is 13. That gives you a remainder of 1, so we're going to use that one. And 27 and 11 is 16. We already used that one, I believe. 27 and 11. Didn't I already use him? Am I out of my mind? 27 minus 11 is 16. Oh, it's right there. Sorry about that. All right, 19 minus 14 is 5, so that works. 19 and 14. 14 and 19. 19 minus 11 is 8, so that also works. Cool. 14 minus 11 is 3. No. So notice that you have 1, 2, 3, 4, 5 things. We're doing 5. Choose 2. which would be 10. Should be 10 pairs times 2 because it works both ways. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Well, yeah. I'm sorry. It's 20 plus these 5 up here are different because you're picking them with themselves. So yeah, 25. There they are. They're all there. This is an equivalence class relation. This is an equivalence class. This is an equivalence class. Okay. So just be aware of that. Okay. Different kind of equivalence classes. We're going to see more of that in section 8.4 with the modular stuff. I kind of enjoy them though. They're almost fun. Yeah. So let's see here. Let's do another one just for a good time, shall we? Okay. So this one here we're going to do. So E is a relation on the integers. You're like, it's the same relation we've seen earlier, Jay. I know. Okay, so it just says that M and N are members of the integers. That's cool. And so the M, E, N is defined such that 2 divides the difference. Cool. Nice. Now what it wants to know is it wants you to prove that it's an equivalence relation. Cool. And describe the distinct equivalence classes of each relation. Okay, so we'll start number 1. First, prove that it's an equivalence class. Okay. Excuse me. Excuse me. All right, so for instance, for proving this, you got to think about this, right? So M is either equal to 2k plus 1 if it's an odd number, if odd, or M is equal to 2k if even, right? Right? So another way of saying this is to say that M is congruent to N in mod 2 is another way of saying this. Okay, well, that's cool. So if you think about this, what are you saying? Well, either they're both even, in which case you're going to have 2k minus 2n, where n and k are integers. Okay, so if that's true, then this could be written as 2k minus n. But k minus n, an integer minus an integer, is also an integer. So I could write that as 2 times, I don't know, big G, where this big G is an integer. And does 2 divide this? Sure does. Okay. If it was the case that they were odd, it would be 2k plus 1 minus 2n plus 1. And when you subtract, you will get 2k minus 2n, which again can be written as 2g. And yes, once again, 2 divides 2g pretty clearly. Okay, so that's how you'd prove it. And then the 2 distinct equivalence classes are, hey, they're both odd numbers or they're both even numbers. Okay, in other words, you could have started off with both odd numbers, or you could start with both even numbers, in which case the odds are an equivalence class and the evens are an equivalence class. Okay, so another way of looking at this problem we just did a minute ago back here. The remainder 1 problems, think about that. The remainder 1 problems could be written as 3k plus 1. I'm sorry, this is just 3k, sorry, because the remainder 0. The remainder 1s would be 3k plus 1, and this would be 3k plus 2. Think about it now. What is, with the exception of these guys here, which give you 0, their differences is equal to a 3k. Their differences were equal to a 3k, I should say. Their differences are equal to a 3k. So 24 minus 11. So 24 is equal to something. Okay, so it's equal to 3k plus something, right? And then 11 is equal to 3k plus something. Is that really 11? Did I do that? Oh, because it's not 24, it's 14, you clown. There's my problem. Sorry. It makes more sense now. Whew. Makes more sense there, dummy. This is 3k plus 2. This is also 3k plus 2. So when you do that, you get 3k plus 2 minus 3k plus 2. And what do you end up with? Well, you end up with 3. Well, not 3k, 3n rather. You end up with 3k minus n. Right? In other words, there's no remainder left over. Down here, these guys had a remainder left over, so you had 27, which was equal to 3k in this case. And you had 11, for instance, which was 3k plus 2. If you take 3k, well, let's do 3n. 3k minus 3n plus 2, what are you left with? Well, you ended up with 3k minus n minus 2. You're left with a negative 2 remainder. Remember, on our mod clock, which we'll talk more about, a mod clock, if you're going negative remainder, it's going this way. That's how we got a remainder 1. Okay? So we say that this thing here is congruent to 3k minus n plus 1, right? Well, yeah, in mod 3. Okay? Or you could just say it's congruent to 1 mod 3. Okay? And then here, you, for instance, 46, which was equal to 3k plus 1, and 11, which is 3k plus 2. If you subtract them, 3k plus 1 minus 3n plus 2, you end up with 3k minus n, of course. Then you get 1 minus 2 is negative 1. But remember, this is congruent to 2 mod 3. That's what's been happening. Okay? So just be aware of that going forward. Kind of fun. For instance, suppose you had these numbers. Hippie. Okay. The equivalence class is on A under mod 4. Okay. Well, again, you could have the 0, 1, 2, 3, and that's it, remainders. This would just be 4k. This would be 4k plus 1, 4k plus 2, 4k plus 3. So which of these numbers can be written that way? Well, obviously 0 goes into this one. 4 obviously goes into this one. There's no 8, so that's it on the top end. And then, of course, negative 4 going this way, correct? So 4k plus 1 obviously gives you 5 on this one. Or, well, 1 first and then 5, clearly. I'm going to scoot it over a little bit. So 1 and then 5. In essence, you're counting by 4s, yes? So 1, 5, 9. Well, there's no 9. Now going back the other way, you're like, wait, if I go back 4, that puts me at negative 3. That's correct. And then go back 4 more, puts you at negative 7. That is correct. 4k plus 2, obviously you start at 2, 6, dot, 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 going that way. Negative 2, negative 6, going this way. Okay. And then 4k plus 3 is 3, 7 on this end, negative 1 on this end, and then negative 5 on this end. Is that everybody? I think so. Negative 6, negative 5, negative so on, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7. They're all there. And those are the different equivalence class relations. Okay? It's pretty easy to do. It's not terribly difficult. Don't overthink it. When you go to prove something to me, and I think there's only one problem I think I asked you to do that on, I'm more interested, can you explain what's going on? Okay? You don't really have to get into a full-blown proof and kill yourself off. I don't care about that much. Okay? And so just be aware of that. It's pretty easy to do, I think. Yeah, I think that's all I wanted to talk about that, guys. So that is your 8.3 section. Good luck to you.